Okay, we're going to complete the discussion of Chapter 5, gases, today. So in your, I don't know, have I posted the first part yet? If I haven't, I might post it together in a single video. But I'm going to back up just a little bit. Just so we kind of refresh your memory and mesh things together. This was the slide for the discussion of the combined gas law. Remember, there are two ways to approach these gas problems. One is as a before and after. You know the conditions before, you know most of the conditions after, except for one, and you can solve for it. Or you can know the conditions after, and you're missing a variable in the before conditions, and you can solve for that. And these are the equations that allow you to do that. Boyle's law by itself here, and we introduce Charles' law into that mix. There's volume, temperature, volume, temperature. Then we introduce Avogadro's law. There's volume, moles, volume, moles. Now we have a before and after situation in which you can have multiple variables. In other words, you can start off with this pressure and into that one, start off with that volume into that one, start off with that moles into that one, start off with this temperature and solve for that final temperature, just as one example. Or if you take this equation and you say, okay, the moles are not changing. That gas is trapped, it's not changing. So you can just, that cancels out and you're left with PV over T. So you can arrange the equation any way you want, just identify which items don't change. Okay. All right, so now we're going to move on. The next slide is a discussion we had on, let's see, the ideal gas conditions. What is an ideal gas compared to a real gas? And I may say a word about that. But before we get to the second slide after this one, I want to just take this equation and play with it. Okay. Now, these two are equal for the same reason that PV equals PV. PV, PI, VI equals PF, VF. Because they're equal to a constant, the same constant. So if this is equal to a constant, and that's equal to the same constant, they have to be equal to each other. Okay? So we can manipulate this equation, or we can just say, all right, both of these are equal to a constant. Call it whatever you want. This leads to a situation where you're in a state, not a before and after. You're just right here and now. You don't know how you got there. And say you know that condition, and that condition, we find out how many moles. Okay? If you don't know the before and after, then you're stuck, unless you know the value of the constant. If you know the value of the constant, then it's like any equation, you can solve for that unknown. Okay, so we're gonna say, let's say our standard pressure is 1 atmosphere. Okay, so let's just pull that out. We know they're both equal to that constant. So let's just say for right now, at this instant in time, the pressure is 1 atmosphere. Okay? And let's say we only have 1 mole. 1 mole of gas at 1 atmosphere pressure. And we're at a standard temperature for gases. For gases, the standard temperature is 0 degrees Celsius, which is 273 K. 273.15 actually. Okay. All other chemical reactions, all their chemical situations, the standard is 25 degrees Celsius. But for gases, it's 0 degrees. Okay. Now, what is the volume of that gas under these conditions? You have to measure it. And as it turns out, it's 22.4 liters. If you have 1 mole of gas at 1 atmosphere pressure and 0 degrees Celsius, then it will occupy 22.4 liters. Okay, so you've got these values that are all correlated for a gas, an ideal gas, and now you are able to calculate what that constant is. Okay, and if I put my numbers up here correctly, that constant should be 0.08206 units of measure. Liter atmospheres per mole K. Okay. Now we have a fixed value for our constant under any conditions. As long as we use these units of measure for volume, liters, atmosphere pressure, moles, of course, and K for temperature, now we have an equation, and we've given this special symbol called R. That's the ideal gas equation constant. And this is the ideal gas equation. It's usually not written that way. Most of the time you'll see it like this. Okay, we just took the moles and the temperature and put them over here. Okay, now we've got a way for a state situation, not a before and after, but right now, because we know that value. Then if you know, say, the temperature, volume, and pressure, and you put them in the right units, they have to be in the correct units to match the units for R. They got to match these units. Then we can solve for the number of moles, for instance. Okay? That's how the ideal gas equation came about. These are the conditions, these are the things we talked about last time for an ideal gas. Right. Remains a gas under all conditions of temperature and pressure. No, that's never going to happen. That's the ideal gas. Has a point molecular volume. Remember math? What a point is? Point has no dimensions. No height, no width, no depth. It's just a point. So when we say point volume, we mean those molecules don't have any volume. It doesn't interact with other gases. They don't attract, they don't repel. And of course, it has to obey all gas laws. Now, real gas, if you cool it and compress it, most gases will eventually turn into at least a liquid, and some of them will go solid, like carbon dioxide. You can turn it into dry ice. I used to do that in the lab regularly, 2 or 3 times a week. Had a cylinder of liquid carbon dioxide, and you blow it through this special apparatus that would cool by evaporation, evaporative cooling. You take that liquid, evaporate it, and get very cold. So part of it would evaporate, about half of it, and the other half would turn to a solid. And it would be at minus 78.5 degrees Celsius. And we throw that in our coolers and take it to the field, and take our plant samples and throw it on that ice, and it would cool fast enough where it wouldn't degrade. Yeah, because as soon as you cut off your hand, it starts dying, right? It's got no more blood supply. Same thing with plants. You pluck a leaf, it's removed from its supply of fluids and whatever comes from the main plant, and it starts to die. And as soon as the cells start to die, they degrade. And we didn't want that. We want to know we were looking for particular biochemicals, of course. And we didn't want them to degrade, so we cooled them in the field like this. As cold as we can get them, as fast as we could get them. Then when we got back to lab, dunk them in liquid nitrogen at -195. And that's where they stayed, at that temperature, until we got ready to freeze dry them. But I digress. You can turn a gas into a solid, or nitrogen you can turn into a liquid. You get it cold enough. That's a real gas. And they do actually have volumes. I'm thinking that can be measured. And they do interact with the other molecules of the same gas or other gases in mixtures. And here's an interesting one. They interact with the walls of the container. Right? Gases have to have a container. If they didn't interact with the walls of the container, we could never measure pressure. You'd never know you had a gas in there if you can't measure the pressure. Okay. Under what conditions do gases behave ideally? Under low pressure and high temperature. Low pressure is 1 atmosphere. High temperature is room temperature. Okay, so the earliest investigators of gases could treat gases as ideal. Even when they first started, they didn't know any different. They just started investigating gases and they found that they all behave the same way at these temperatures and pressures. Okay, it wasn't until we started compressing them in very high pressure and decreasing their temperatures that we saw that gases really weren't behaving ideally under those conditions. But high temperature, room temperature, 1 atmosphere pressure, all gases behave alike. Okay, now the ideal gas equation, I've run through that derivation. It was first proposed by Emil Clapeyron in the early part of the 19th century. You might see his name again, where gases are involved. Not in this chapter, but maybe later. So there's your ideal gas equation. And this just says that R value can have different units. Now, I chose these units because it fit the explanation. Liters, atmospheres, moles, K. And when you use those units, you always get this value. But if you use different units, like if you keep moles in K, but you change to pascals and cubic meters, which becomes joules. Joules per mole K, then you get a different value because you use different units of measurement. So it's important that if you see this R, and it's universally accepted as the gas constant, it appears in numerous other equations that may not look on the surface like they have any relationship to gases. Do you need some handouts?
Yeah.
Okay. No, interrupt me. You can't fly without swim without your floaties, right? Not in these waters. There you go. This is the lab. That's what we're doing today. Review documents. Okay. I don't have an instant replay, so I don't know where it was. Let's see. Constants. Yeah. Oh, that's right. You'll see this R value in numerous other equations. And it's important with any constant value that's introduced into an equation and is pre-existing the variables, like this one is. Right. It's there before you determine these values. Then these values have to be converted into compatible values for the constant. You have to know what the units of measure for that constant are. So this one, we generally use in equations that involve energy transformations because the joules in there. That's energy unit. Okay. And both of these are in your useful information at the back of your review document, which means they're available for the exam. Okay, let's see. What did I mean by this statement? If R is not used, if you have an equation that doesn't involve R, and I suppose I'm referencing earlier before and after equations, where you have PV and R, PV and NT, and no R's, then you can use any units of measure for pressure, for volume, and of course, moles is a given, but there are other units that we're not messing with right now. But temperature always has to be K. Now, do you remember why temperature has to be in K units? One word starts with an S. Sign. You don't want your temperatures with negative sign. That just muddies the water. You can't get a valid calculation with negative sign. And even if even if both your temperatures are positive, sooner or later you're going to end up with a negative situation. Plus, the ratio is not based upon this relative position of, say, Celsius. It's based upon absolute value from here to there, or from here to here, or from here to there. 0 is absolute. So these before and after equations, and for the state equations, they will not work without temperature in absolute units. And for us, that's K. Okay, so this equation can be rearranged in a multitude of different ways. And this is just an animation to show that you can rearrange the equation for the unknown. Right? There's one here. Let's see. Let's do T, and then there's another one right after this. Here we go. Suppose what you need to know is not necessarily just one of those variables. Maybe you need to know the ratio of variables. Just solve for the ratio. Right? If, say, we want the ratio of moles to volume, then you just solve for these. Now, that doesn't tell you what the volume of the moles would be, unless you know one or the other, but it does tell you the ratio. It just means that you can solve this equation any way that's required. Okay, and there we solve for R, and plug in those values that we talked about earlier, you'll get this one right here. Okay, example. Calculate the pressure. This system is in state. How do you know it's in a situation of state and not before or after? Because there's only one unit of moles here, only one temperature, only one volume, and it's asking for the pressure. It's not giving you two values of any of those. It's just single values of each of those that go into the equations. So it has to be a state function. You can't solve it any other way. So if we want to calculate the pressure, first thing we do is say, okay, this is a gas solution equation. This is I'm mixing my terms. Not a solution in the chemical sense, but solution to the problem. If we're trying to solve a problem, we've determined that it's a state. Then we look for the question, calculate the pressure. Then we say what equation are we going to use? Okay, it looks like this one. We use that one because we have moles, we have temperature, we have volume, we have our gas constant. We're going to solve for pressure. Next thing you do is check your units. What are the units? Okay, moles, good. Degrees Celsius, bad. Add 273 to it. Liters, good volume. Okay. Now, when you solve it, the pressure is going to come out in units of atmospheres because the constant is liter atmospheres per mole K. So in this case, we're going to rearrange the equation for pressure and plug in our numbers. Right. There we've changed to K, right, with that calculation. And let's see, I need parentheses around those, don't I? That's this one times that one. Cancel units, and we're left with atmospheres. Okay, so a gas under these conditions, that much gas at that temperature and in that volume, will exhibit a pressure of 1.018 atmospheres. Okay. If you open the valve, what's going to happen? At sea level, you're going to hear as some of the gas comes out because it's just a little bit more than 1 atmosphere pressure. Okay. How about we want to calculate the moles of gas contained by 150 liters at minus 15 C and 850 millimeters of mercury. Okay, we know the pressure, we know the volume, only the pressure is in the wrong units. Got to convert that to atmospheres, right? Divide by what? 760 atmospheres. Then we add 273 to this one. There's a negative number. If you stick that in the equation, what are you going to get? You're going to get a negative value. So there's an example of negative numbers bad. And then we rearrange the equation for, well, after we convert standard units, of course. There we go. And then we solve for moles. All right. And we discover after canceling units that we have 7.918 moles of gas. Now, this is good instruction because, let's see, I'm going to do that. Where's our syllabus for the lab? Yes, we are. We're going to use the gas law to determine the number of moles of a gas in the container. And while we're at it, we're going to find out what the mass of that gas is inside the container. Mass, moles. We're going to be able to calculate the molar mass of a compound. It has to be a volatile compound. We're going to do it at boiling point of water, roughly. It's called the Dumas method. And that's one way to get the molar mass of a compound, and you don't even have to know what the compound is. Right? Remember when we were doing composition calculations, empirical formula, molecular formula, or maybe not molecular, yeah, molecular, that's good enough. What do you need to know to go from empirical to molecular formula? You need to have an independently determined molar mass for the compound. Because the empirical mass is not necessarily the molar mass of the compound. This is one of the ways you can do it with the Dumas method. You can determine the moles of the gas and the mass of it, plus the molar mass of that gas, without even knowing what the gas is. Okay, it's just one method. There are numerous methods for doing that. And it just depends on the nature of the compound. Okay, so more of that later. You can also use the gas equation in stoichiometry. Find out how much reactant was required or how much product was produced. if you have a balanced equation. In this case, we've got a reaction where mercury 2 oxide is heated and produces liquid mercury, a little shiny beady stuff, plus oxygen gas. The question is, how much mercury 2 oxide was decomposed in this reaction to produce 220 cubic centimeters of oxygen at 25 degrees Celsius and 740 millimeters of mercury? Okay, so remember, when you have a balanced equation, if you want to move anywhere in that equation, what do you need to know? Moles. Got to have moles. In this case, do we have enough information to find out the moles of gas? Because if we know the moles of gas, we can convert it to any of those other units in there, any of those other reactants or products. All we need to know is how many moles of gas are produced in this reaction. Well, we've already converted 220 cubic centimeters, which is what? 220 milliliters. Convert that to liters. Right, just move the decimal place 3 on the left. Gives you liters of oxygen. Okay, we've got volume. We need to convert that to atmospheres and convert this to K. Right. There we have values. We have 3 of the 4 values we need because we already know the constant. Plug them in and find out how many moles of oxygen that is represented by these conditions. So we plugged in the values: pressure, volume, R, temperature. It turns out, after we cancel units, oops, there we go. We have a small number of moles. 8.8. What's going on here? There it is. 8.755 times 10 to the minus 3 moles of oxygen. So now that you know the moles of oxygen, you can find out how many moles of mercury 2 oxide were required during that reaction. Mercury 2 oxide is red. It's a bright red. And of course, you know that it's kind of like that copper sulfate, hydrated copper sulfate was blue, and then when we heated that blew off the water, it turned white. Well, in this case, the reactant is red, and it turns to silver. So you see a color change. All right. So we use the coefficients for our conversion factor. And now we know this gives us the number of moles of mercury 2 oxide, and this converts moles to grams of mercury 2 oxide. So we're chaining those 2 conversions together. And that gives us 1.87 grams of mercury 2 oxide required to produce that. Now we could just as easily find out how much mercury there is in that container. What was one assumption that we had to make? This is a closed container, right? So how about the volume of those solids? In reality, do they make a difference? Yeah. This occupies a certain volume, and this occupies probably a little less volume. So we're assuming that the volume doesn't change during that reaction, right? But we know it does. So we're close to the right answer, but not right on it because of that error that we've introduced. Now, how do we minimize that error? Well, let's see. We have 220 milliliters, so that's not very big. If I wanted to really minimize the error, I would take those same conditions and I would giant size my container. Yeah. So on a percentage basis, the volume of the solids means very little. But then You got to be sure that you can make the other measurements also. Temperature, of course, shouldn't be a problem. Pressure, can we measure the pressure? Yeah, we've got devices that will measure the pressure inside that container. It'll be a lot less than that because the volume is increased, right? Pressure and volume are inversely proportional. So if I increase the volume like this, then the pressure is going to go down. So you got to be able to measure those things. Okay. So what was the original? Calculate the mass of this one needed to produce. Okay. Calculate moles of oxygen produced. What volume of mercury was produced? Okay. In order to do that, we need to know the moles of mercury. And this is our conversion factor. So we've got to find the mass of mercury. So notice that we have the same number of moles as mercury 2 oxide. We already know that value. And we just need to convert that to mass of mercury, and then we can use this conversion to find out the volume. Okay, now we're converting it to mercury. And then we're going to convert the mercury to mass. And then we're going to convert the mass to volume using its density. Okay. So let's see. 0.258, how many liters is that? That's 2.58 times 10 to the minus 4th liters. 10 to the minus 4th liters versus 10 to the minus 1st liters. So it probably has a little impact on our calculations for that gas. But now that we know the volume, we can make that adjustment up here and see if it makes a difference. We can do that. Lots of stuff we can do. Okay, here's the Dumas method I was talking about earlier. Using the ideal gas equation to determine the molar mass of a volatile liquid. And what we mean by volatile liquid is at a moderately increased temperature, above room temperature, we can convert that liquid into a gas. If you can do that, then you can use the gas law because we're still at low pressure and high temperature relatively. So we can use the gas law to determine how many moles of gas is contained in that vessel. Right? It was first proposed by this fellow right here. It's obviously a Frenchman. He's not the same Frenchman, that's Dumas. He's not the same Frenchman that wrote the Three Musketeers. Okay. It's a different Dumas. Kind of like, I guess Dumas is kind of like Jones or Smith. The country's full of them. Dumas was pretty active in other areas also. Organic chemistry, he was very active there. They probably used this method in his organic analyses. Let's see. And originally, the method was based upon the density of the vapor that was produced by turning a liquid into a gas. But that's kind of cumbersome. I mean, you can still do it, but I think our method is easier and more understandable, actually. If we do it the way I described earlier. What we also want to do is look at these two equations. Now, you can determine the mass of the gas by weighing the container before and weighing the container afterwards. That's easy. You get the mass. You need the number of moles. That's the part that requires the gas equation. So if we're going to use this equation, we can find moles and then plug it in this equation, or we can combine the equations, right? Use a little algebra. So if we do that, I think we've got an animation here, so I don't have to write on the board. All we have to do is convert, solve this one for moles and plug it in this part right here, plug it in that equation. That's it. Now we've got mass and molecular weight together. Molar mass, molecular weight, that's what I call it. So then once we plug that in this equation, right, and we solve for the molar mass, then now what we have to do is find out what the mass is, find out what the pressure, the volume, temperature, the universal ideal gas constant, plug them all in there, and it spits out that number, molar mass, in one calculation. Okay. Good to go? Finally, it just dawned on me that I was moving a little fast. Okay. Here's an example. I mean, that's a lot of words, but basically what you got is a flask like that, and the flask has a volume that you have to measure. How do you measure the volume of that flask? Well, the easiest way is to pour water into it, right up to the brim, and then dump it in a graduated cylinder. Okay? There's another way you can do it. You can weigh the flask dry, then fill it with water, weigh it again, and use the density of water. By difference, you can find the mass of the water. Use the density to calculate the volume. It's another way. So once you know the volume, then, and we put some liquid in here, that's our compound, and then we cap it. We double cap it. Why do we do that? Because we're going to submerge it in boiling water. Boiling water. So the vapor that comes off of that water, we're going to try to condense on these cool surfaces. So we put an extra cap around it, and we don't use that cap in the weighing process. We weigh the dry beaker with the inner cap on it. Dry. Then we put the other cap on it, and we poke a pinhole through both of them. Right? We don't want a big hole. We want a pinhole so we don't have any reverse currents set up. We want this to vaporize like that and fill that entire container with this compound. Expel all the air. Nothing in there but the compound. That way, as it leaves that vent hole, then it stabilizes eventually at atmospheric pressure. Right? So we need another pressure outside because that's going to be the pressure inside. It eventually stabilizes. Once you've used all this up and it's filled with vapor only, then it'll stop venting. And the pressure inside is the barometric pressure outside. We measure the volume. How about temperature? The temperature of the gas inside is the same as the temperature outside. By conduction, all that gas is heated to this temperature. So we know pressure, volume, temperature. We can solve for moles using the gas equation. Now, how about the mass of that gas? Well, after you get finished with this experiment, you pull that cap off, the outer cap, and then you take that whole apparatus and dry it. and weigh it. You weighed it before with that intercapital dry. Now you weigh it afterwards. And when you take it out of the hot water, of course, you're going to let it cool to room temperature because the balance will get swirly if you put a hot object on it. But once it's cooled down, what's going to happen to that gas? It's going to condense into a liquid again. But how about the mass? Is the mass going to change? No. The mass of the gas and the mass of the liquid are exactly the same. And air is going to rush back in here to fill the space. But you weighed that air before because it was inside there when you weighed the dry container, correct? So the difference between before and after is the mass of that condensed gas. Now you have the moles and the mass. You can calculate the molecular weight. Okay. That's the Dumas method. And the reason I went through all that explanation is because if you just look at all this stuff right here, it'll make your head spin. There's too much there without understanding what it means, what each one of these things mean. 250 milliliter flask. Okay, there you go. With a pinhole lid. Okay. Ours was a double lid. Weighs this much. Dry. Then we put an excess amount of the substance in there and dunked in boiling water. There's your temperature. And barometric pressure was this value until all the liquid evaporated. Now you only have gas in there. How many moles of that gas do you have? Let's just use these values and you can figure it. Because the temperature is not the cool temperature. The temperature is the hot temperature. Okay. Then you let it cool, of course, and wipe it dry and weigh it. And the difference between this and that is the mass of that gas. And you're ready to roll. Right? And that's what all this is about right here. We use the combined equation there to find molecular weight. Plug in the values. And we get 152.98 grams per mole for this example. Okay. What kind of problem is this one? Is this before and after a state? 50 liters is the volume, final volume of the gas. Consider the problem, calculate the final volume of gas when 50 liters of the gas at this temperature and this pressure is cooled to this temperature and that pressure. That's obviously a before and after. So you got to decide which one do you need? Well, what if we write the whole equation up here? Right? Initial. Final. So what do we have changing? Well, we know we're going to calculate the final volume when we know the initial volume. So we got this one, and we're going to calculate that one. So we got to keep those. Temperature, we're going to cool it from 250 to 25. So we're going to go from there to there. Pressure, and the pressure is 750 millimeters of mercury first, compressed to 900 millimeters of mercury. So the pressure here and here are known. What didn't change? That one. You don't need moles. We trapped the gas, and we didn't let it loose until the experiment was over. So the number of moles stays the same. So now that you know before and after, and if you have any problems translating this information into this equation, then write it down first. Just do it like this. Pressure first, pressure second, volume initial, volume final, temperature initial, temperature final. And just put your values there. Then you can plug it into the equation without making a mistake. It takes an extra minute or two to do that. Now, do we need to convert? We do need to convert temperature. That's obvious. That's always the case. But how about volume? Well, the volume is liters, so the answer is going to come out in liters. How about pressure? Do we need to convert that pressure? No. We said on a previous slide, the only one you have to convert is temperature. When you're before and after, because it's a ratio, right? And the units will cancel. It's only when you're in a state function that you need to take care of all the units to match the constant units. But in this ratio situation, the before and after, the only one that you have to be certain to change is temperature. The rest of them, you can leave them as is. And if the unknown is, if the unknown were millimeters of mercury here, and you solving for this one, then the answer would be millimeters of mercury. If you convert it to atmospheres, then the answer would be atmospheres. Okay. So in this example, I think this complicates things. I inherited this slide set and I have completely modified it. This just means that before and after are equal to the same constant. We already talked about that. So you don't need the constant. You just need to solve for your final volume. And we're going to get rid of, should have got rid of moles. Oh, we are going to do it in this step. Right. Moles before and after cancel, right? Because they're the same. So then we solve for them. I got 23.75 meters. What else is wrong with this picture? Little L. Supposed to be a capital L. So I got some work to do on this slide set. Okay. How about, let's use what we know in this equation. This looks like the reverse of the Bosch process, the Haber-Bosch process. We're going to decompose ammonia to nitrogen and hydrogen gas. What's the final pressure of a system when cubic feet of ammonia at this pressure and this temperature is rapidly heated to 500 degrees and the vessel expands to 30 cubic feet? We can calculate the final pressure. That's a before and after. The only one we have to be converting is temperature. Okay. So here we go through that rigmarole and we find out there's our pressure, plug in our values. The trick to this one is moles. Before and after are different moles. See? Start off with 2 moles gas on this side. These are all gases. You got 1 plus 3 is 4 moles here. So the moles do change in this situation because we conducted a reaction in which all of this is decomposed into that. So all of these 2 moles became all of those 4 moles. So there you have the arrangement here. 2 moles of this gas, 4 moles of that gas final. And that will give you. Now, if you got a problem like that on a test, what would a devious instructor do? He'd say, make that one 2 and that one 2. What answer do you get? Put that in there as a selection. Because if you make that mistake, you're going to see your answer there, but it's the wrong answer. So the moral of that story is multiple choice tests are not as easy as they look. So watch out. So this would be actually, I put in a value that's half that. If I wanted to put in a selection that was wrong, one of them would be half that value. Okay. You thought we were finished with laws? No, we got one more very important law. It's Dalton's law of partial pressures. Remember John Dalton and the atomic theory? That wasn't the only thing he did. He also noticed that when you measure the total pressure of a mixture of gases, remember a mixture of gases is always homogeneous. It always makes a solution. That mixture can be subdivided into the individual pure substances, the pure gases. And each one of those gases contributes to the total pressure. That's the partial pressure of that gas. If you had only that gas in that vessel under all the same conditions, it would be less than the whole, but proportional to how many moles it is. So if you have twice as many moles of nitrogen in the container as you do oxygen, then if oxygen is measured at partial pressure 1 atmosphere, nitrogen would be 2 atmospheres. And the total would be 3. Okay. So when we look at it that way, the total pressure is equal to the partial pressures of each one of the gases. And we can express the pressures of each one of those individual gases in the mixtures in terms of the universal gas equation, or the ideal gas equation. Okay. So this is total pressure. This is a representation of the total pressure. The total number of moles times the gas constant times temperature divided by volume is equal to that pressure. But if you subdivide it and you say, well, let's see, I have so many moles of this gas and so many moles of that gas and so many moles of that gas, each one contributes its own pressure to the total. And each one, since they're the gas, that's a constant, they're all at the same temperature, they all occupy the same volume. So the only difference among the gases that makes that pressure difference for each one of them is the number of moles of each one of them. So if we rearrange that equation, right, there's our total pressure, each of the different pressures here. I should have put this one first. It would have made more sense. Then we can factor out the common terms. R, T, and V are all the same. So that factors out and it leaves the summation of the moles. So really, the total number of moles is equal to the sum of the individual moles, and they're all proportional to pressure. Okay? That partial pressures. So we have a new unit of measure called mole fraction. It's real simple. It's just the number of moles of the individual gas divided by the total moles. That's it. It's a fraction. So it's always going to be, for a mixture, each mole fraction will be less than 1. If the mole fraction comes out to be 1, what does that mean? That means it's pure. Right? It's not a mixture. Because that's the only thing in there. Right? The total divided by the total is 1. So if you have a mole fraction that's less than 1, you know it's a mixture. And there's the calculation for each one of our examples, each one of those 3 gases. And then if you add up all the mole fractions, it should be 1 or very close to it, within very narrow, small amounts of experimental error that's possible. So here's an equation that's all gases. We're saying this is a gas, carbon dioxide, water vapor, nitrogen, oxygen, all gas. But what is that? You really can't tell from that formula. I have to tell you what it is. That's nitroglycerin. So 4 moles of nitroglycerin as a gas decomposes explosively. I mean, it's really fast. And it goes from 4 to 12 plus 10, 22, 28, 29 moles. It goes from 4 to 29 moles of gas like that. That's why nitroglycerin is so good as an explosive. They call it what do they call it? The speed of the blast wave. Right? The faster the speed of the blast wave, the more effective the explosive, more power it can deliver. Because power is energy delivered per unit time. The shorter the time, the more power. Okay. So, we took a very, very small amount of this stuff and put it in a 100-liter vessel. Gives it plenty of room to expand at this temperature and this initial pressure, 20 millimeters of mercury. So we almost evacuated the cylinder. And that would also confirm that this is a gas, because nitroglycerin is at room temperature and pressure is a liquid. So under these conditions, it would be a gas. And we detonated it. And apparently the vessel is allowed to expand, so it must have a removable cylinder. And the cylinder expanded from 100 to 110 liters. And the temperature rose to 400 degrees from 25. So it's also an exothermic reaction. So the question is, calculate the pressure. What's the pressure, final pressure? Well, let's see. What do we have? This is before, and after is our unknown. This is before liters. This is after liters. Volume, volume, volume. This is after temperature. This is before temperature. Right there, right there. And then the moles is start off with 4, and we expand to 29. Okay. So in order to do this, we don't need to know what mass of this we put in there. Right? All we need to know is these conditions of the gas. And we can calculate that the pressure went from 20 to 297 millimeters of mercury. Okay. So it's still a partial vacuum, but it's quite a bit increased. What is it? What's 20 into 300? 15 times increase in pressure with only a 10% increase in volume. Okay. So if we know, we can calculate the partial pressures of each one of these in that vessel. Right. We have to assume that all of this disappeared. And now we've only got these. So what's the ratio? The mole fraction of the gases is the ratio of their coefficients, right? So 12 of those 29 moles is carbon dioxide. 10 of them, 10/29ths is water, 6/29ths is nitrogen, and 1/29th is oxygen. So we can use that knowledge there for carbon dioxide. It's this fraction of the total. The mole fraction times the total pressure will give you the pressure, the partial pressure of each one of these gases. And you can do that for each one. Down, down, down. Is that it? Yeah, oxygen, that's the last one. Add them all up. And we add them up to 297.59. And we started off at 297.61. Rounding error. Okay. Now, we talked about laws this whole time, gas laws. Just what happens. Now I'm going to explain why it happens. This is the kinetic molecular theory of gases. And the interesting thing about it is the kinetic molecular theory of gases has since been expanded to include other phases, liquids and solids. Once we understand gases, then we can translate that into useful theoretical discussions of what happens to solids and liquids as well. But it all started with gases. These are the basic postulates of the kinetic molecular theory. This is what we're saying. We have to consider large numbers of particles, atoms, or molecules, or both combined. Individual particles in a gas, large numbers. Why? Because we can't treat them as individuals. We don't have the computing power or the detection power to monitor every single particle in a gas. So we treat them statistically. That means for the best statistics, you need large sample size, right? So that's what we have here, large sample size. We also say that the particle size is small compared to the distance between them. But there's a lot of space between these atoms and molecules. They're in constant rapid motion, and random motion by that actually included. Right? We do a calculation in a few minutes that shows you just how fast they are moving. But they move that for short distances, and then smack into some other gas molecule. When they do collide with one another, or the walls of the container, they act like billiard balls. They just bounce off each other. Right? We're treating them as ideal particles. In other words, they don't interact. They just obey the laws of physics, right? Conservation of momentum and so forth. And these collisions are perfectly elastic. Anybody had any physics in here? Elastic collision. Elastic collision means that we also conserve energy. That is the kinetic energy of this one moving in, this one moving out. The total kinetic energy, bam, after the reaction is the same as before. We don't lose anything in the encounter. As opposed to an inelastic collision, right? Remember, well, you can do it with Play-Doh, but I used to use silly putty. When you take silly putty and you drop it on the floor, it just goes like that. Instead of bouncing back up, it just goes. That's a silly putty. You know, silly putty does bounce, doesn't it? Okay, Play-Doh. Play-Doh's better. You get a ball of Play-Doh and drop it on the floor, it just goes. That's an inelastic collision. Right? The energy that it acquired in its fall is dissipated at the bottom, turned into heat. Okay. These particles also collide with the walls of the container. That's how we know they're there, because they register pressure. And we're also saying that all the gases in the container have the same average kinetic energy. That's another statistical tool. And it's measured by temperature. Temperature is a measure of the average kinetic energy of all the particles in a substance. In this case, a gas. And they're all at the same temperature. Now, in reality, we know that's not true. But we're going to treat it that way for simplicity's sake. And I mentioned this one earlier. There's no interaction between particles. When they collide, they just bounce off each other like billiard balls. Okay, we're going to use this example, right? I said we couldn't track individual particles, but we're going to expand those particles to the size of a bowling ball. And each one is 5 kilograms. Right? That's roughly the size of a bowling ball, isn't it? Something like that. Between 10 and 15. Does anybody use a bowling ball bigger than 14 or 15 pounds? Some people do, probably. Or kids. Kids are like 10 pounds. Or 8. Tiny people. Anyway, we got 7 of these balls. And we're going to calculate the kinetic energy. Here it's E sub K. I always write KE. And we're going to use the formula. Kinetic energy for each one is equal to 1/2 mass times volume squared. So we're going to do that for each one of these balls. right? So we need information. We need to know how fast are they moving. They're all 5 kilograms. So they're moving at different velocities. Right? We said earlier that the kinetic energy of all the molecules is the same, the average kinetic energy. In reality, we know it's not. I mean, each individual has a different kinetic energy. But the average is what? Well, let's see, if this one's moving really slow and that one's moving fast relative, then we calculate individual kinetic energies here. So what's the average kinetic energy of all of those? Right? That's what this is. No, this is average velocity. Excuse me. These are the individual kinetic energies. Right. What is the average velocity? Let's do that first. Because if we know the velocity, the average velocity, then we can calculate kinetic energy for the average speed. And the average speed is 40 meters per second. But before we do that, let's calculate what the average kinetic energy is. Right? Take the average of that column. Right? So there we do. We just add them together and divide by 7. We get 5,000 joules. Right? That's what kilogram meter squared per second squared is, a joule. Right? Kilogram meters per second squared, so meters squared per second squared, is a joule. So when we do that, this is actually the average kinetic energy. We know that. 5,000 joules is average kinetic energy for these balls. There's the range, there's the average. What if we calculated the kinetic energy using that value? What would we get? There we go. Oh, excuse me. We're actually going to take this value and say what speed or what velocity is required to give you that kinetic energy. So we rearrange the equation and solve for velocity. And it turns out, in order to give you this average velocity, you need this value for the average. But to give you this average kinetic energy, you need this average velocity, 44.72 meters per second, not 40. So see the discrepancy? If you go from these values here and you calculated the kinetic energy from that, you would get something less than 5,000, which would not be average kinetic energy. So we need another way to measure. We need another way to determine the average velocity that will allow us to calculate the kinetic energy on average. And the solution is called root mean square. I don't know if you've ever heard that before. I'm going to explain what it means. Root mean square. Let's see. No, not yet. Hold that. Root mean square. The best way to understand this is to work backwards. So you take all of your values, like we had 10, 20, 30, down to 70, right? Take each one of those and square them. So this would be 100, 400, 900. This would be 4,900. Square those values. So this is the velocity, this is velocity squared. Squared. Now take the mean. So the mean of these values is something here, whatever that happens to be. Okay? Square the values, then take the mean of the squares, then take the square root of that mean. Like that. If you do that, back up. If you do that, you will get this value right here. The root mean square velocity will go into this equation and give you the average kinetic energy for all those particles. Okay? Now, you've used root mean square your whole life and didn't even know it. Right? I'm going to tell you where it is. It's right there. Power. The power that comes from that plug is alternating current. That is, increases over time, 60 times a second. It increases in voltage. And then it goes back down past 0 voltage, and then the negative of that. It's a sine wave. It goes like that, 60 times a second. It does that track. If you try to do calculations with any of those values, I mean, you have to freeze it at an instant of time. We can't do that. Right? So when we use our physical laws to determine power, for instance, consumption, you need an average value that reflects the voltage that it would be if it were direct current, that is coming out steady direct current the whole time like that. And the way you do that is you take the root mean square of all the measurements in that one cycle. Okay. So it'll go up to, let's see, I measured this one time. The root mean square voltage coming out of that socket is 120 or 115. But if you measure it, it peaks out at about 150. And then it goes down to negative 150. It goes backwards and forwards. So for calculation purposes, we use 115. Equivalent voltage. That's the root mean square voltage of that sine wave. Okay. So I just made that point because I didn't want you to think this was some exotic calculation. I mean, you guys have been using it your whole life and didn't even know it. Okay. Oh, I told you I was going to run long. Unfortunately, the lab doesn't take a long time. So we've got a few extra minutes. If you can survive. So for a mole of particles, we would need to know the energy, the kinetic energy in all three axes, right? This way, that way, that way. And this will be the calculation for each one of those vectors. That's the fancy term for it. It's a vector. The root mean square velocity takes all those averages into account, those root mean square averages into account, and you're not going to have to do this calculation. I'm just leading up to this value right here. The root mean square velocity, and this mu, this little mu, is used because it's not really velocity. It's a root mean square average, right? So we use mu instead of v. So we take this calculation here, and that gives us our root mean square velocity. Now, what can we do with it? Well, for a large number of particles, that root mean square velocity is equal to the square root of 3 times, there's your R, gas constant, temperature in Kelvin divided by the molar mass. So what that means is, since this is in the denominator, right, as the molar mass increases, its velocity decreases to have the same energy at that temperature in the mix. So if you have a mix of helium and neon at the same temperature, then the helium is going to be moving a lot slower, a lot faster than the neon. Okay, that's what that means. But we don't stop there because we can use, well, of course, this R has to be the one with energy, so it's a different value. We can use that information to, one, calculate the average speed of the molecule air. Right. So I'm going to give you the fast version. The velocity of air is molecular weight of air, which is the weighted average. And we calculate that to be 516 meters per second or 1,100 miles per hour. So those molecules of air are moving faster than the speed of sound. Notice also, when you use this formula, because that R is in terms of kilogram meter squared or joules per mole K, the joules has within it kilograms. It's part of the measurement. So that means this molar mass has to be converted not from grams per mole, but kilograms per mole. If you don't do that, you're going to be off by 1,000. Okay. So that's what it is for air. For helium, it's a lot faster. That's why when you suck in helium and try to talk, the pitch goes up because the molecules are moving faster. And I understand you can also do it, decrease your pitch if you inhale the right gas. But it would have to be a gas that moves slower than air. Okay. So one last law. This is Graham's law of diffusion. And it allows us to relate two different gases, a known gas and an unknown gas. And we relate the velocities of each of the gases. There's gas A and gas B. When we ratio those, velocity times time is distance, right? And that's equal to, right? Here's the velocity for A, there's a velocity for B. Since they're both under the square root, we put a square root over both of them. 3RT is the same for both, it cancels. And then we flip this one on top because what? The denominator of the denominator is the numerator. Right? This is in the denominator. When we bring it into the numerator, it flips over and becomes on top. Now this is the denominator. The denominator of the numerator is the denominator. But the denominator of the denominator is the numerator. So that's why it ends up looking like that. And it makes sense because the ratio of the velocities, right? The lighter one moves faster than the heavier one. So we need to invert them. They're inversely proportional to their molar mass. And this relationship, either velocity or distance traveled, right? If you measure them over the same amount of time, then you can use distance instead of velocity. And here's an example. Let's see. Where is it? Oh, okay. So when we have these two gases, hydrogen chloride and ammonia gas, that's HCl is not in solution, so it's not hydrochloric acid. It's hydrogen chloride. When you put those in cotton balls, you stick them in the ends of a glass tube. Then when they meet, they're going to diffuse through the air. And when they meet, they produce ammonium chloride, solid. So they make a fog right where they meet. And you can measure the distance traveled. Right? And the ratio of the distance traveled should be 1.463. So if we do that experiment, see, is it going to do it, or do I need to touch another button? Touch another button. There we go. That's where they meet. The faster moving one is the lighter one, which would be ammonia. Ammonia is lighter than hydrogen chloride. So ammonia moves over here, and the ratio of these two distances is 1.463. Okay, you can use that relationship for an unknown compound. And you can determine, if you make it the unknown, you can determine its molar mass using this method. Right? You just have to be sure that you have a way of measuring those different distances. Right? And that's what this slide does, and I'm not going to spend a lot of time on it because we've run out. But we can do that, and we determine that the molar mass of this unknown gas is, from this list, the closest one that comes to is hydrogen iodide. So instead of hydrogen chloride, hydrogen iodide gives you the same fog, similar fog. Okay? A practical application. Purification, separation of isotopes of uranium during World War II. We needed U-235. Most of uranium is U-238, which does not fission. 235 is the one you need to make a bomb. Iran knows that. That's why they've got their ultracentrifuges running day and night, trying to make a bomb. They're using centrifuges and the difference in mass between the atoms, right? The lighter atom will be more toward the center. The heavier atom will be thrown to the outside. So they just suck off the center, send it to another centrifuge, and repeat that over and over and over again until they get better than 90, 95% U-235, and then they make a bomb. But that wasn't the only way historically that separations were done. The US government during World War II knew we needed a definitive way to end the war. And one way was to make a weapon that was so powerful and so intimidating that the enemy would surrender. So they printed vast amounts of money, and they investigated different avenues of creation and purification of these isotopes. One of those ways used Graham's law. So if you take uranium and you convert it into a fluoride, that allows you to make a gas out of it at a much lower temperature than if it were uranium metal. So you can make a gas out of it at an elevated temperature, and the mixture, you push it through a sieve. And the 235 is going to go through faster because it's lighter, right? It's moving faster. So you have these sieves stacked, and each time it goes through a sieve, it's enriched in 235. So you just have thousands and thousands of them stacked. By the time you get to the end, you have enriched U-235. Okay? The problem was you couldn't make your sieve out of just anything, not even stainless steel. Uranium hexafluoride would eat it up. It would corrode stainless steel in minutes. Fortunately, this fellow right here, Plunkett, had been playing around in the lab, he and his team, and they discovered Teflon. Turns out that Teflon is impervious to fluorides, probably because Teflon is a fluorinated hydrocarbon. It already has all the fluoride it needs, so it doesn't want any more. So they made these at this plant in Oak Ridge, Tennessee, called K25. They had these stacks and stacks and stacks of sieves that were made out of Teflon. Very, very, very tiny holes. It needs to be very small holes. And you can tell from the size of the plant, this is like 44 acres for that one building. They needed lots of sieves to do the purification. I used to live in Oak Ridge after the war, of course, in the 50s, early 60s, and they were still operating these plants. And they were monstrous. They had barbed wire fence around them, and the guards had orders to shoot first and ask questions later. So we just used the access road around the outside. And for family entertainment, because we didn't have a lot of money, we just all pile in the car and we drive around that plant. It take about 20 minutes. And you could look in and see it in the distance. You know, it was a ooh-ah for the kids. But there were other plants in Oak Ridge that used different methods of separation. But this one applies to our study of gases. And that should be the last. Oh, sorry, one more item. We can use the ideal gas equation to characterize and solve the equation for real gases. But you need correction factors. And those correction factors were proposed. This is old information. They were proposed by this man, Johann Dieterich van der Waals. He got the Nobel Prize for it, his studies of gases. And his equation took, this is the pressure component right here, PV equals nRT. This is the volume component, and there's nRT. So the pressure correction requires that you use moles of gas in the volume, and this experimentally determined value, A. You also need this experimentally determined value, B, incorporated here to give you a volume correction. If you know those values for your particular gas, then you can solve this equation for very high pressures, very low temperatures. Now we're done. And take a break and I'll meet you in the lab.